All right, in this unit, we're going to talk about two different ways to graph, which is graphing polar equations and graphing parametric equations. You're going to find these are very different from the kinds of graphing that you've done up to this point. So all of the graphs that we've done before, we graphed in what we call the rectangular coordinate system, which is also called the Cartesian plane because it's named after René Descartes. So what we're going to look at now is a different type of coordinate system, which is the polar coordinate system. This uses circles and angles to plot points and graph functions. This may make you think a little bit of the way that we use bearings to show direction. It's similar, but not quite the same. So the way that we plot points in the polar coordinate system. So remember back when you first learned graphing, you had to learn about the origin and the x-axis and the y-axis. This is no different, okay? So the foundation of the polar coordinate system is that you start with a horizontal ray that extends to the right. This is called the polar axis. The end point of this ray is called the pole. So if you see in figure 6.19 there, the pole is the end point of the ray. The polar axis goes to the right. This is just like how we would always have to put our initial side when we graphed angles in standard position. This is just like on the unit circle. R represents a directed distance from the pole to P. So the fact that it's directed is important because if R is positive, then I want to go to the right. If R is negative, then I want to go to the left or opposite of wherever I might have drawn that ray before. Theta is an angle. It can be in either degrees or radians from the polar axis to the line segment from the pole to P. So just like on the unit circle, positive angles are measured counterclockwise and negative angles are measured clockwise. So a polar coordinate is the point P is r comma theta as opposed to x, y, which is what we're used to, okay? So if we look at this graph down here at the bottom, the point 135 degrees is shown there. So R stands for radius. So what you'll see when you see these polar graphs is you have sort of an X and Y axis. We're not graphing in X's and Y's, so it's not really the same thing. So you can think of it as your north-south line and your east-west line. And the marks along the polar axis there, 1, 2, 3, represent circles of different radius lengths. So the point 135 degrees means that from the polar axis, which is this right here, we want to rotate 135 degrees, and the point should be 2 units away from the center. That's how we get that point right there. The circles, we don't draw the circles. That's just kind of there to help us, just like the grid marks on an XY graph are there. Those grid marks don't really become part of the graph. It just helps us visualize where we're going. So here's some examples of points that we can plot using polar coordinates. So the point 3 to 70. So again, we're always going to start on the polar axis, which is this one right here. So we have the pole, which is the center or the origin, and the polar axis. We need to rotate from there 270 degrees, which is going to take us down to here, and we need to plot our point 3 units away from the center. So this would be the point 3, 270. Now, if the radius is negative, here's how we're going to work with this. We need to think first, where would the point be if r was positive? And then we reflect it. So this one says to go to the point -3, 3 pi halves. Well, 3 pi halves is also down here. So 3 pi halves, I would normally go to this point right here, but because of the negative r, it's going to bounce it back to the opposite side. So that point there is the one that we want because of the negative radius. Okay, so take a second and see if you can plot that third point yourself. Now, something tricky about number 3 here is that this is fourths, and our graph doesn't have fourths marked on it, but we know that fourths are halfway. So here's a fourth, here's a fourth, here's a fourth, and here's a fourth. So negative pi fourths would mean I need to rotate this direction. This is going to be the value negative pi fourths, and I need to be on that ray. So normally I would put the point right here, but because it's negative, I need to reflect it in the opposite direction. Typically that angle is going to be this one right here, but we want to be on the opposite side of that angle because of the negative radius. Okay, so this would be your final answer, is this point right here. Okay, because of the way we know that circles work, that you can rotate infinitely many times and still land at the same spot over and over and over again. That's why we say you're going in circles, because you keep coming back to the same spot. So here's what's different about the polar coordinate system. In rectangular coordinates, there's only one way to represent getting to the point x, y. However, in polar coordinates, there's infinitely many ways to represent the same location. So the point r theta is going to be equal to r theta plus 2 pi. Any multiple of 2 pi is going to be a coterminal angle, and so it'll land at the exact same spot. So r pi halves is going to be the same as r 5 pi halves and the same as r 9 pi halves or negative 3 pi halves. Any multiple of 2 pi is going to take us to the same spot. Or because of what we know about a negative radius, we could go and just change by a difference of pi and then reflect our radius back. So any multiple of pi, as long as you change the sign of the radius, is going to give us another way that we can write this point. Okay, so here's a few examples of how we could rewrite the same point in multiple different ways. So we're going to have the point 5 pi fourths, and we want to rewrite this in 3 different ways given these conditions. So the first one is that r stays positive, so that means we need to keep it as 5, and theta is between 2 pi and 4 pi. So that means that to do that, we need 5 pi fourths plus 2 pi. That's going to get us into this interval right here. So that would be the ordered pair 5, 9 pi fourths would be the polar coordinate. That is going to be the exact same point as 5 pi fourths. Okay, now here's another one. Let's say that we want r to be negative and we want theta to stay between 0 and 2 pi. Well, we can do that as long as we switch the sign of r and add only 1 pi to pi fourths. So that gives us the ordered pair 5 pi fourths. Or sorry, negative 5, okay? And then take a second and see if you can think about C on your own. We want r to stay positive, but we want our value of theta to be between negative 2 pi and 0. So for this one, we keep r positive. In order to get it down to be a negative, I need to do pi fourths minus 2 pi, which gives me the ordered pair 5 negative 7 pi fourths. All of these ordered pairs will plot the same exact location, okay? So that is worth knowing. There is a relationship between polar coordinates and rectangular coordinates that allows us to convert back and forth between the two. Now, this has everything to do with what we know about the right triangles in the coordinate plane and what you know about your unit circle. So this is all information that we want to keep in mind. So first, let's talk about how we convert from polar to rectangular. So we have an r and a theta, and we need to get to an x and a y. So the rule is this: to find x, x is always equal to r times the cosine of theta, and y is always equal to r times the sine of theta. Now, again, if you want to know why, I would refer you back to this. We know that the sine of theta, for example, is equal to y over r. If you multiply by r on both sides, we get r sine theta is equal to y. Same thing with cosine. So that's where these relationships come from. So let's look at the first one. We have r and theta right here. So to find x, we're going to do 3 times the cosine of pi. And to find y, we're going to do 3 times the sine of pi. Cosine of pi is 1, so that means x is equal to 1 times 3, which is 3. and the sign of pi is 0, so y is equal to 0. So this ordered pair in rectangular coordinates is the point 3, 0. That locates the exact same spot. Now let's think about what that looks like, okay? So if I graph the point 3, 0, 1, 2, 3, 0, this is supposed to be -1, so that makes this -3. Sorry about that. Make sure you correct that. The cosine of pi is -1, not +1. Okay, so 1, 2, 3. The point -3, 0 is here, and in polar, we would want to rotate pi on this circle that has a radius of 3, so we would land in the exact same spot. Okay, pause your video and go ahead and try number 10 on your own. I'll be back with the work in 3. Okay, so you should have -10 cosine pi 6, which is -10 times the square root of 3 over 2. And that gets us simplified to -5 times the square root of 3 as our x coordinate. And in a similar way, we get -5 for our y. So our ordered pair is -5 root 3, -5. Okay. Now, it's helpful to be able to go the opposite direction as well. So if I have a rectangular ordered pair and I want to convert it to a polar coordinate, then the first thing that we do, I don't know why this kept numbering 3, 4. This should say 1, 2 again. Whoops. Okay. So the first thing we need to do is figure out the value of r. We do this just the same way that we did on the unit circle. So it's the square root of x squared plus y squared. And then to figure out the value of theta, we use the fact that tangent of theta is equal to y over x. And we will have to work backwards to solve for our value of theta. So let's look at an example. So for number 7, the first thing we need to do is figure out the value of r. So we have our x and our y here. So r is going to be equal to the square root of -1 squared plus the square root of 3 squared. That gives us the square root of 1 plus 3, which is 4. So r is equal to 2. We don't need a plus or minus because we're talking about a length, okay? We'll choose the positive value there. Now, to figure out theta, we know that the tangent of theta is equal to y over x. So that is the square root of 3 over -1. Okay, so this is where we have to consider the quadrant. Remember, this is always important. So with our rectangular coordinate, the ordered pair -x positive y is going to be in quadrant 2. So that means here we need to choose a theta value that is in quadrant 2. Where is the tangent equal to -pi3? Well, not pi3, square root of 3. Tangent is equal to square root of 3 at pi3. So to get into quadrant 2, that would be 2 pi3 is the answer that we are looking for. We need to make sure that our answer is in the same quadrant as the ordered pair that we talked about. So now we know our ordered pair, r theta is 2 pi3. Okay, pause your video and try the last example yourself, the ordered pair 2, -2. All right, so for r, when we get this radical simplified, we get 2 root 2, and then we find that the tangent of theta is equal to -1. So again, we now have to think positive x, -y tells us that we are in quadrant 4. So we need the theta value where tangent is negative that is in quadrant 4. So it's equal to -1. It's going to be a fourth. So we have 3 pi4, that's in quadrant 2. We need 7 pi4 because that is in quadrant 4. So our ordered pair is 2 root 2, 7 pi4. And so that is how you can convert back and forth. And that's where we'll stop for today.